are online, so we'll be using this particular method of communication. So I'll start explaining something, and then when I need your feedback, I'll ask you to write. This way, you will also stay awake. Okay. So we're going to go a little quickly because there's a lot to cover and only around an hour. So let's just get right into it. Can you see my screen? Okay, I haven't shared it. It should be visible now. Okay. So let's start. So you all must be familiar with ChatGPT. It's all the hype since like 2023 begin, and now there are more models than you can count on 10 fingers that do large language modeling. And the idea of how does text goes to ChatGPT or any model for that matter, and how can you get these kind of results that the AI is showing now is what we are going to talk about. So we just want to see how you can format text data such that your models can interpret them. So the before we like get into the meat of the matter, let's understand a few things first. In the world of computers, everything is binary, right? Whether you want to represent a number, whether you want to represent a text, whether you want to represent an image, whether you want to represent a video, whatever it may be, everything at its core is represented as binary. Now, before we start talking about the current representations of text and more specifically about the representations of text for language models, we need to sort of first go back a little and talk about what were the classical text representations. So it's not like text is something new to computers. It is something that has always existed. So in 1963, we had the ASCII standard. I hope everyone knows about this. So it was a 7-bit representation for representing text. So you have like you have eight bits, and 7 of them are reserved for representing text. And it formed a total of 128 characters. Now that was a limited set because ASCII covered only special characters, numbers, and then the English alphabet in uppercase and lowercase. And then people realized that the 8th bit is a wasted bit, so they added more characters. So now you have 255 characters, which is the extended ASCII set. Then as the need of computers grew, and it's not like English is the only language in this world, so people came up with a different standard for representing text, that was Unicode. So Unicode sort of came into being in the late 80s. 1988 is one year that sort of people can agree upon. This is the current standard for text representation. Now, Unicode is different from ASCII. So it is a variable length encoding. You can reserve up to 4 bytes to represent text, and you start with just 8 bits initially, and then if you need more, you can go 2 bytes. If you need more, you can go 3 bytes. And then this standard sort of extends to UTF-8, UTF-16, and UTF-32. Now, again, these representation of texts are just so that the computer, when it's processing something, it can identify something as text. The idea for a model, a machine learning or a deep learning model to understand text goes beyond this. Now, if anyone has ever worked with neural networks, or let's say even a classical machine learning models, you'll realize that the input to these models is usually numbers. It's not the models do not take any kind of text input. So it's not like I can feed my name directly into a model. It has to have a certain numerical representation. And in the machine learning terms, we like to call them vectors. So the input to the models are vectors. Now, uh, this is what we think about when we think of vectors. This is what we are classically taught. You have three axes, x, y, and z, and a vector, let's say in this case, a three-dimensional vector, would have some component in the x direction, some component in the y direction, and some component in the z direction. But now, how does text, let's say you write your name, I write my name, how can I represent my name in this manner where it has an x component and a y component and a z component? So that basically does not make any sense. So we will now start building upon how can I represent my text, which is, let's say, a name or anything, in that vector. So this is going to be the premise. Now, before we start talking about converting text to vectors, we first need to understand text a little bit more. Let's start with a very simple sentence. A quick brown fox jumps over the wall. Now, this is a very common sentence that I guess everyone who has ever done anything with HTML or CSS or any random string that you want to generate, this is the most popular of those strings. So if you look at this sentence, I can split it into its tokens, which is quick brown fox jumps over the wall. So these tokens are basically the words which comprise these sentence. Now keep in mind the word token, because we will now be addressing these atomic units of text as tokens. Now, when you start understanding textual data, it is not like you're always looking at one single sentence. When we talk about text data in while dealing with an NLP task or any machine learning task, we usually have a data set. That data set would be made up of multiple documents. Let's say I want to process the birth certificates of babies in a hospital. Now, in a hospital, there can be multiple babies that are born, and if you make it more complex, like I want to analyze the data from, let's say, 10 years, uh, from 2010 to 2020. So that means you have a lot of documents that will be present in that data set. Each of these documents are textual now, and each of these text documents will consist of multiple tokens, right? And when you combine all the tokens across all the sentences in a document, across all documents, you'll get what's known as the vocabulary. So the vocabulary of a data set is a set of all the tokens present in that data set. Is this clear? Does that make sense? You can type a yes and let me know. Okay, good. If at any point you feel I'm making things a little too complicated, just let me know. Okay. So this is basically how text will be processed. So two things that we need to take away from these two slides is the word token, which means an atomic unit of text, and the word vocabulary, which is a set of all the tokens within the data set. Now, the idea is we need to convert a text, let's say my name, into a vector. So how do you do it? As I already explained, the classical vector is something like this. You have A of I cap plus B of J cap and C of K cap, where A, B, and C are the magnitude and I, J, and K are the principal axis. Now, what we want is something like this. You have an axis along one token, you have another axis along another token, you have another axis along another token. So for each of the tokens in your data set, or let's say in this case, for each of the tokens in your vocabulary, you need an axis to represent it. And then if you combine all these axes, you will get a larger word vector space. Now, one cannot really come up with something like this. I mean, I cannot start thinking about a word vector space as a numerical data space or like a multidimensional space of numbers. So we need to still continue to think about it in a different manner. So there is one model which is called the bag of words model. Now, in this, you consider your entire vocabulary as the vector space from which you will be sampling vectors for each of your tokens. Now, again, as this graph shows, each token here would be one of these axes, and each sentence can be represented as a vector in that space along these tokens. So, to sort of demystify this, let's start with a sample data set. So I have a sample data set here. It has three sentences. So the data set goes like the movie was superb. That is the first sentence. The second sentence is I liked the movie. The third sentence is the movie was okay-ish. If I generate a vocabulary out of this, I'll see that there are only 6 words in the vocabulary. Superb, was, liked, okayish, movie, and the. These are the common words. There should also be an I, but for some reason it's not here. Now, once I have this vocabulary, I can sort of represent my sentences as one hot encoded vectors of this vocabulary. So, what I mean by that is, this is my entire vocabulary. The I liked movie was super okayish, right? This is my vocabulary. Now, let's look at sentence one. So, sentence one was the movie was superb. So, it would have the, it would have movie, it would have was, and it would have superb, right? And for all the other values, that is I, liked, and okayish, it didn't have any of these, right? So if you compare this representation with this representation, you will see that wherever you had a component or wherever you had a token, the magnitude was 1. Wherever you did not have that component, the magnitude was 0. So the in the first sentence you had the, so magnitude is 1. You had movie, so magnitude is 1. You had was, so magnitude is 1. You did not have okayish, so magnitude for that is 0. Similarly, for the second sentence, the sentence is I liked the movie. So you have magnitude for the I liked that movie, and you have no magnitudes for the other 3. So this is how the bag of word models work to represent your text as a vector. Did you understand this? Okay. So yes. So currently, in this example, we are considering a sentence. So think of it as this. So if you just want to represent a word, like in this representation, it does not make sense to just represent a word. I know we will talk about word embeddings when we uh, go deeper into this. So currently, now for this particular example, you cannot really represent only words, because if I say the, then it's actually a component. It's actually a principal axis. So like I cannot write a vector as I cap. That's not really a vector. I mean, it has to be like either one I cap. So it means like a unit in that direction. But this would really only make sense when we talk about entire sentences. That makes sense? Okay. 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 So this is the very basic way of understanding word vectors, which is the bag of words model. Now there is an issue with the with this kind of an encoding. I'll talk about what the issue is. So the first issue is sparsity. Now, if you look here, the vocabulary is of size 7. That means for each sentence that I encode, the vector would be of size 7, equal to the size of the vocabulary. And not every sentence that I represent will have all those words, right? So you see that this sentence had 4 words and 3 were 0. So almost 50% of the sentence is empty because like those words do not make up that sentence. So it's a sparse vector. Uh, Compound this problem that if you have a vocabulary size of 1000 tokens and each input sentence contains only 20 tokens on an average. So you will have a vector of size of 1000 components where only 20 components of that vector would be contributing to the vector, and the other 880 vectors don't contribute anything. So that is one of the problems. Now, why is this a problem? Is because when you represent this in your systems, it would take up a lot of space, right? Think of this as an array. So you have an array of uh, length 1000, and out of those 1000, you're only using 20 indexes. And this is for one sentence. If you have 10 sentences, the array size becomes 1000 times 10. And in production, you will have around, say, 20,000, 30,000 sentences. So then again, that big of an array. The other problem here is that there is an equal weightage given to all the tokens. Now, when we talk about language modeling, there are certain tasks which require you to focus on certain aspects of the language itself. So let's say if I was running a sentiment analysis of this data set here. Now, if I read the first sentence, which is the movie was superb, if I remove the words the and was, I am left with movie and superb. If I just read this as movie superb, I am still getting a sense of what that sentence is trying to convey for the sentiment analysis task. Similarly, liked movie, I can remove I and the, and for the third sentence, I can again remove the and was. So they still, even without these words, they still tell me the intent of the sentence, which is my task. But if you see here, you either get 1 or 0. Some words should have more weightage than the other, depending upon the task that you're trying to achieve. Here, you get 1 if the word is present and 0 if the word is not present. So the, was, movie, and superb, they all sort of have a similar weightage. Then the other problem that exists is that there is no order preservation. Now, the first sentence is the movie was superb. This makes sense. The second sentence is the I liked movie. Third one is represented as the movie was okay. Okay. So the first two make sense. The second one does not make any sense because in this representation there is no sort of care given to how the words appear in the sentence. So your context goes away. And if the vocabulary size increases, and let's say someone decides to sort that vocabulary on the strings, so let's say anything that starts with A will come first, and B will come first, and C will come first. So when that happens, if you construct a vector from that vocabulary, all your words would be jumbled up. So that means there is no order preservation, and this means that the semantic meaning between the words go away. Now, we can sort of start handling these problems one by one and come up with ways to solve them. So the first thing that we need to address is the sparsity problem, because that is sort of the most pain point in terms of the space that is required to store all that vocabulary. Now, there are some pre-processing techniques in NLP that are used to remove sparsity. So the first thing that we do is called stop word removal. So there are certain words within the data set that don't hold much meaning when it comes to the NLP task. So as I already explained, if I removed the and was from a sentence, I can still identify what that sentence is trying to tell me. There's a similar example here. I ate a banana, and I want to do like an action classification task, like what action is mentioned in this sentence. So I can just remove I and and I will still have 8 banana. So 8 banana tells me that whoever is the subject of the sentence ate a banana. So I can remove I and these are my stop words. And you'll see that most sentences contain these stop words. So removing them, what will happen when you remove them? Let's go back here. if I remove I, the, and was from this, I automatically reduce my vocabulary by half. So now the only words that remain are like, movie, superb, and okay. Similarly, there is another process called stemming and lemmatization. So you may come across words that have different representations, right? Let's say the word amazing. Some people say amazing, some people say amazing with like multiple G's in the end. Some people say amazingly, right? Everyone writes differently. But if you see, the root word here is the same, which is amaze, right? All of these representations of a single word can be handled by either substituting them with a single stem or substituting them with a word from which they originate. So let's understand this with more examples. So in stemming, what you do is you basically just clip the words and maintain the common part. So here I gave this example: amaze, amazed, amazing, amazingly. They all convey the same meaning. What they have different is the tense, and like one is an object, one is an adjective, the other one is a verb or a noun. Sorry. So the stem here is amaze, which is AMAZ, right? This is the stem. Now I can just replace all of these tokens by amaze. And so let's say if the word amaze is written differently in all my different sentences, I don't need to store all these four tokens. I can just replace them with just one token. So I'm again reducing my vocabulary size. Similarly, there is this process of lemmatization. Now, the problem with stemming is that stemming, what it is doing essentially is it is clipping the word. So that may not really, uh, mm, what it will do is it will not preserve the meaning of the word at times. Consider this example. So historical, historically, and historian. The stem here is history, which is fair enough. You can use the stem as well, but you can also use the lemma of it. So lemma is history. This is the base word from which all of these other words originate. So you can either stem your words or you can lemmatize them. Now there's also a catch with stemming and lemmatization. Stemming is actually a faster process because it is a heuristic based process. Lemmatization, on the other hand, it's a learned process. So you will have something like a WordNet lemmatizer, which is a model. You will input your corpus to it, and it will then determine what will be the lemma of each of the word in your corpus. So stemming is faster, lemmatization is slower, and sometimes you might also need to lemmatize, like train your own lemmatizer or fit the lemmatizer on your own set to get like better lemmas. And there is no this thing like you cannot choose key, okay, stemming is better and lemmatization is not, or lemmatization is better or stemming is not. That completely depends on the task at hand. But these are a few techniques that will solve sparsity, but they are still not good enough. They are good as pre-processing tools, but we can still think of other options that will solve the sparsity problem. Okay, so do you understand what I have said up until now? Are there any questions? So everyone understands what I have explained? You can type in yes. Okay. So it seems that only one person understood. Everyone else is in awe. Okay. Why we are not using other? Okay. So the idea is that we will come to those methods as well. This is just an introduction of how you can think about encoding text, and then I discuss the problems with that. So the problems tell you that, okay, maybe there is a new need for another encoding method, and we will jump to that in the next slides. Any more questions? So we'll continue with the next topic. Okay, so now the idea is that we introduce another method. So previously we saw bag of words and one hot encoding. Now there's another method that we will introduce to represent uh, text as vector is TF-IDF, which stands for term frequency inverse document frequency. Now the vectors of TF-IDF have certain characteristics. So the first one is that the tokens that come out of TF-IDF, they have weightage. In one hot encoding, we saw that every token had the same weight, and if it was present, it would have a weight of 1. If it was absent, the weight would be 0. This is the first problem that we faced in one hot encoding. The second problem is that the vectors were sparse. With TF-IDF, we also solve this problem of sparsity. Now we don't solve this right away, but I'll tell you how this will happen. So let's break down TF-IDF. So TF-IDF consists of two parts. First is the TF part, which is called term frequency. Term frequency for a document is calculated only for the tokens of that document. So what is the term frequency for a token? It is the count of the token. Let's consider one single sentence. So count of token for that sentence, how many times did the token appear in that sentence, divided by the total number of tokens in that sentence. Inverse document frequency is different. So let's say you consider a token. Now, what are the total number of documents divided by the documents in which that token was present, right? And then you take a log of this division. I know the formula straight away does not make sense, but once we start with the examples, we'll see things in more clarity. Again, let's start with an example. So we'll consider this sample data set. It has 3 sentences. So the first sentence is, I like all kinds of fruit. Second one is, I like all kinds of fruits, but I like pineapple more. And the third one is, I do not like any kind of fruit. So let's process them through the TF-IDF method. First thing that we'll do is apply the pre-processing. So all the stemming or the things that we learned just now, that is stemming and stop word removal, let's do that. And the minute we do that, you'll see that we already have reduced the total number of tokens in our set. So the first sentence just translates to like kind fruit. Second one is like kind fruit like pineapple. And the third one is not like kind fruit. Now we calculate the term frequency matrix. Now, as I said, term frequency is the count of a token in that sentence divided by the total number of tokens in the sentence. This is calculated for the entire vocabulary. So the vocabulary now consists of like, kind, fruit, pineapple, and not. You can construct the vocabulary from here. So we have like, kind, fruit. These are 3 words which are repeating in all the sentences. So we have 3 words. Then we have pineapple and not. So only 5 words in our vocabulary. Now for the first sentence, the total number of words in the sentences is 3. Like appears once, kind appears once, fruit appears once. So this is their term frequencies. Pineapple and not do not appear. So this is their term frequency. In the second sentence, there are a total of 5 words. So like appears twice, kind appears once, fruit appears once, pineapple appears once, not does not appear. In the third sentence, the total number of tokens are 4. So 1, 1, 0, and 1. So this is the term frequency matrix for these sentences. Is this clear? Okay. Now let's go to the IDF values. Now IDF values are not calculated for sentences. These are calculated for each individual token in the vocabulary. Now, like, as I mentioned, this would be log of total number of documents divided by the documents in which the token appears. So there are total 3 documents, and in each of the document the word like has appeared. We can just verify this. The first sentence has like, second sentence has like, third sentence has like. So the IDF value for like would be 3 divided by 3 and then log. Similarly, kind also appears in all the three sentences, and the total number of sentences is also 3. So log of 3 by 3. Similarly, fruit is 3 by 3. Now pineapple only appears in one of the sentences. So 3, which is the total number of sentences, divided by the number of sentences in which pineapple appears, which is 1, and you take the log of it. Similar case for not. Now, when I want to create my TF-IDF vectors, what I would do is that I would take this TF matrix and I would multiply it with this IDF matrix. So then I would have these values. Now, these are 0 because like, kind, and fruit have IDF values of 0 because log of 1 is 0. So for all the sentences, like, kind, fruit would be 0. Now pineapple and not are not present in the first sentence, so that TF values are 0. So it is 0 multiplied by log 3, 0 multiplied by log 3. Here pineapple is present, so 1 by 3. Sorry, 1 by, it should be 1 by 4, 1 by 5 actually. So yeah, so this value is 1 by 5 multiplied by log 3. So it comes out to be 0.1. This value is 1 by 4 multiplied by log 3. So 0.12. Now, just looking at this and compare it with the one hot encoded matrix. If this was a one hot encoded matrix, sentence 1 would look like 1 1 1 0 0. Sentence 2 would look like 1 1 1 1 and 0. Sentence 3 would look like 1 1 1 and 0 and 1. But here, if you see, it has completely changed, and the values are no longer 1 and 0. They are somewhere between. So you are also seeing like these decimal values. Now let's look at these vectors and start asking someone whether they like fruit or not, and what can we infer just from these vectors. So from the first sentence, we don't get any indication of whether this person likes a fruit or not. So it doesn't really matter, even though the sentence says that they like, I like all kinds of fruit. So that means it either doesn't matter or they like everything. It's sort of a ambiguous kind of a statement. From the second statement, you can clearly make out that the person likes pineapple. And from the third statement, you can clearly make out that the person does not like any kind of fruits. Now, the question arises is, why does TF-IDF work in the first place, right? Now, there are few there are few reasons why this works. If you look at what term frequency is doing, term frequency as a value is telling you how important a token is in a particular document. So term frequency is calculated document wise, and it tells you how many times the document a token appears in a document. So if a token is appearing multiple times in the same sentence, that means it might be important. On the other hand, what IDF does is that it determines how important is a token to distinguish between two different documents. So if you have two sentences, right? Let's say like, kind, fruit, not like, kind, fruit. Consider the first and the third sentence. The only thing that differentiates the two is not. All the other words are appearing in both the sentences, but the only differentiator is not. So what IDF does is that it suppresses this behavior where all the things that get repeated too often between sentences are suppressed, and the things that are uncommon between the sentences get highlighted. So it's like a discriminator. That's a bold claim, but you can think of it like that. Now, due to these features, TF-IDF works really well when you have tasks where you want to calculate similarity or dissimilarity between the sentences. Now we can start talking about the pros and the cons of TF-IDF. So the first thing is that it is really good at calculating similarity and dissimilarity between documents, because as we saw, it sort of suppresses the words that are common between the sentences and do not provide any information, and they highlight the words which are different between two sentences or documents. Now you can also reduce dimensionality. How can you of your vectors? How can you do that? Now let's say on uh, this particular matrix, if I apply a threshold that, let's say, if like has all the TF-IDF values for this sentence, for this token is 0, I can simply remove it because it is not providing me any information. Similarly, for kind, I can remove it. For fruit, I can remove it. I can just remove these values and just restrict myself to pineapple and not, and I'll still be able to do the calculation that I want to. So immediately you remove the three tokens from your vector space and you are left with only two tokens. Now this is one way, that is you apply a threshold on the TF-IDF values and you remove the tokens that you don't seem to that don't have any significance for your task. Now the other thing that you can do is you can apply PCA. I'm not sure how many of you know what PCA is. So PCA is a dimensionality reduction technique. So what you would do is you will try to calculate correlation between these columns here. Those that are closely correlated, you will bunch them together. Those that are not closely, like, so these columns would have different correlations with each other, right? And then once that fall below a certain value, you will just remove them. So your matrix will reduce in size. And I mean, PCA in itself is a different like topic. We can spend an entire session on that. So I won't get into much, but yes, you can use these techniques to reduce the dimensionality of your final matrix or your final vector space. There still, however, is one problem that remains unsolved, which is that this is still not capturing any semantic relation between the tokens. So as one hot encoding was agnostic to the placement of the tokens in the sentence, similarly, even TF-IDF is agnostic to the placement of tokens in the sentence. Okay, is this clear? Can you, like, if it's clear, you can type yes. If it's not clear, you can. Are there any questions? Okay. Right. So I think not. Okay. So now the third problem that is still unsolved is the ability to inject any context. Like, okay, if I say like and pineapple together, what really means is that I like pineapple and I want you to focus on like and pineapple together and not separately. So there is a concept called n-gram, which is basically nothing. It's nothing complicated. It's just basically taking a bunch of tokens and putting them together and saying that, okay, this is one single token. So as I said, TF-IDF will only focus on the tokens that are present. So it will look at each token as a singular token. It will not try to combine them together to form a context or any semantic meaning between them. But what I can do is I can club these tokens together. Let's say this is your example sentence, I like sandwich. I can split it into tokens, I like and sandwich. And then I can create an additional token, which is a combination of like and sandwich. So like sandwich is now treated as one single token. So now your final tokens would become I like sandwich and like sandwich. So you will start treating this as an individual token, and then you will go through that same process. Like, okay, in how many sentences does like sandwich appear as a token or as a word together? Then you calculate your TF and IDF. Now the n in n-gram stands for the total number of tokens which are combined together. So bigram means that two tokens have been combined, like we did here. You can have trigram, and you can just go on 4 gram, 5 gram, 6 gram. The when you do something like this, you also run into the risk of introducing sparsity, because let's say if I start considering all the possible 2 gram tokens in this sentence, I would have I like sandwich, then I would have I would have like sandwich, right? So I now have 5 tokens instead of 3. If I consider all the 2 gram and 3 gram tokens, I would have 6, and 4 gram is not possible. But the idea is that as you keep increasing your bigram and trigram tokens, the sparsity will also start increasing, because then you can have like many combinations. So the recommended number for n-gram is usually uh, trigrams. So if you have like sentences which you are working on for any kind of natural language task, you can go up to 3 gram tokens. So start combining like 3 tokens together and treat them as a single token. If you go beyond that, like 4 gram or 5 gram, it will then introduce the problem of sparsity again. Now, this is all good. So far what we have seen is two methods of representing text as vector, and specifically what we talked about up until now was representing an entire sentence as a single vector. Now I want to introduce another concept which is called word embeddings, and for that we will not use the slides, we will go somewhere else. Now, the idea with word embedding is, instead of representing my entire sentence as a vector, maybe I can represent each word as a vector, and then to represent a sentence, I can combine these vectors together. Okay, so everything is clear up until now. Okay, so let's talk embeddings. Now, the idea is that I want to represent a single word as a vector. Now, why would I want to do something like that? Vectors provide us with very fun things to do with them. One of the things that I can do with a vector, let's say A vector and B vector, is that I can perform some sort of arithmetic on them. So I can do A vector plus B vector, I can do A vector minus B vector, I can do A vector dot B vector, I can do A vector and I can do a cross product. And all of these arithmetic operations will have some meaning to them, right? Now, I want to do something similar with my text as well. Consider this example. King, that we all know what king means. If I subtract man from king and I add woman to it, that means I get queen. Why is that so? Maybe because king is man plus royalty, and from this I am subtracting man. So man and man gets cancelled, and royalty plus woman gives queen. I would like to do this kind of arithmetic with my words, because this is allowing me the freedom of creating meanings, extracting meanings from words, and then creating relations between words, right? So how does that happen? Now, to understand this, let's start with a problem first. The major problem in language modeling is to predict the next word that you see in a text. So let's start with a sample text. Again, let's go back to this thing, which is quick brown fox. Okay. Now I have this text. What I want to do is, if I remove these words from here and replace them with blanks, can a computer solve them? This is called the next word prediction task. Now, how you proceed with this is, you start with a model, you feed one word to it, let's say you feed it quick, and you expect it to output brown. Now, in the training step, if the word was brown, you basically backprop and say that whatever weights you used for predicting brown were correct. If it predicts, let's say, jumps, that means the weights that were used were incorrect, and then you go and you backprop and adjust the weights accordingly. This is a very high level view of what the next word prediction task is. Now, again, to do next word prediction, as I already mentioned, that your neural network would take a numerical input. That means quick has to be represented as a vector, something like this, 0.46, something like that. Now, how do you do that? So this is where embeddings come into play. So let's just start talking about them. Now, the first thing that we want to do is I want to create my vocabulary. So I have quick, brown, fox, and let's just have 4 words for now. Quick, brown, fox, and jumps. Let's assume that I want to represent each of these words as a vector of size 8. So I would have a size 8 vector. Okay. First component, second component, third component, fourth component, fifth component, sixth, seventh component, and eighth component. This is the vector for quick. Brown would have a similar vector, right? A fox would have a similar vector, and jumps would have a similar vector. And when I have my neural network, I will input this vector. So you just send it here, transpose it, and you get your vector here. 1, 2, 3. Okay. So you take this vector, you feed it to your network, you get your output. So after quick, you should get brown. If you get brown, well enough. If you don't get brown, you do your back prop, and then you do another back prop here, and you update these weights. As you are updating these weights, you can also update these vector values here as well, right? So I can start with a matrix of vectors. So let's say my vector size is 8 and my vocabulary size is n, capital N, however many words I can have in my vocabulary. So I start with this matrix and I randomize it. So let's say I set every uh, element, like I set every cell here to 0.5. So I initialize a matrices with 0.5. Then I start doing this next word prediction task. As the model learns and I get the feedback that whether I predicted the correct word or not, the model weights update. Similarly, my uh, this matrix of embedding also updates. This is called the embedding matrix, and this is a trainable matrix. So this is how word embeddings work. So once the model is completely trained, what you will have is a final matrix here that will have one vector for all your words in the vocabulary. So you will have a vector for quick, you will have a vector for brown, you will have a vector for fox, jumps, so on and so forth. And this embedding matrix is what forms the input layer of any of your language model. primarily a deep learning language model. So this is the let's say this is the current representation of text for models. This is what is currently being used for all the models that are in production and that you are using, ChatGPT, Llama, Claude, what have you. This is what will form the basis of the input. Now you can ask me questions regarding this. I know this is sort of a little too heavy. If you don't understand model training, then this part would be a little difficult. So are there any questions? If you understand, write yes. If you have any questions, you can write them or you can ask them.
So Vimal, you mentioned like we have like a matrix of words, right? Embeddings, and then we
Yeah.
try to predict the next word, and based on whatever we are seeing in training data, we are actually back propagating and trying to get the right word out next time, right? So like, is that the only way, like, or can we use embeddings that we already have? Does it always have to be like, if you can throw some light on that?
Yeah, yeah. Okay. So now that's a good question. So now this is how you create your own embeddings. Now, if anyone is familiar with the concept of say transfer learning or yeah, I think transfer learning. So in transfer learning, what we do is that we have a model. Uh, so we have a model which is developed by someone else, and we try to feed it our data. We fine tune some layers of the model, and we keep the other layers as they are, and we sort of now get this model working for our data. So we get output and we are happy. In the same way, we can use embeddings from different models. So let's for this example, let's just consider ChatGPT. So ChatGPT, it has various embeddings which are available. So I think you have Ada, you have DaVinci. These are different embeddings. Now, when I say embeddings, what it means is that this is going to be your ChatGPT model, which is going to be a very large model. This model will have an embedding layer here, right? And I can just isolate this embedding layer. I can put my words in this embed. I can basically process my words through this embedding layer. So take this out of the model, give it my word. Let's say I'll give it my name, and whatever output it gives me, I will take this output. Now, one question that might appear here is that I trained my data. So I trained here on a limited corpus. So there might be a word that might be skipped and it is not present in the embedding. In that case, what would happen? So usually when we do these kinds of tasks, what we try to do is we try to mention a special token, which is called the OOV token or out of vocabulary. So what out of vocabulary token does is that whenever it sees a word which is not present within its vocabulary, it would reserve a vector for it, which of course gets trained, and this vector gets returned for every word that is not present within the vocabulary. Sometimes people also prefer to just ignore that word altogether. If there is no embedding for it, you just don't process it. But usually the way to do it is that you have a OOV token for that. I hope that that answers your question.
Yes, Vimal, it's clear.
Uh, Anyone else has any questions? So first of all, please tell me if you understand this or not. Because if you don't understand it, then I can. We still have time. I can go over it. You can type a yes or no in the chat. Yes means you get it. No means you don't get it. Yes. So Vishrut, you can yes, you can train your own model for embedding. So the process that I described, is the same process that you will follow. So you will consider a corpus of text. Let's say, so I have this book with me right now. I will take this book and read all the text in it. Then I will create a vocabulary out of it. I will set up a next word prediction task. So once you set up that next word prediction task, you will just start with a embedding layer which is like initialized randomly, and then for each word you will make the prediction. During the training step, the embedding and the model will get trained, and once the training is complete, you can extract the embedding layer separately, and you will get your embeddings. Okay. So I'll like also share some additional resources other than the talk. So some time back, I wrote this blog on the same topic. So if you need like more text on this same, you can read the blog. And I also implemented a small research paper search engine which leverages embeddings. So you can go through the code. Now this code has two parts. The first part is where you take the raw data, uh, pre-process it, and create embeddings out of it. And the second part is when you can query those embeddings. So you can take your own text query and convert it into an embedding and do a similarity search against the data present in the database. There are few other things that you will learn from this code is that there is a use of vector databases. So you have classical databases which are NoSQL or SQL databases, and then there are vector databases. So what vector databases do, and this is very high level. So what vector databases do is that they store embeddings. So they will store your sentences or your words as embeddings, and then you can directly query them for queries like similarity search, which is sort of the most common use case with vector databases. And the other thing is that in this particular implementation, I have not trained my own embedding, but used embeddings from sentence transformers. So you will also learn how to use embeddings from a different source. So you can refer to these two materials as well. Yeah, so that is mostly it. There is not really